Dear friends, we are now going to see what is called an AVL tree. Of course, named after these three people, Adelson, Welsky, and Landy. So it is a binary search tree, an AVL tree. So here is a property, a binary search tree in which the difference of heights of the right and left subtrees of any node is less than or equal to 1. So we know what is a balance factor. A balance factor is a difference of heights of left and right subtree. So you can take the balance factor value as the difference between given a node. For example, for this node, if I look the balance factor, the difference of height between this left subtree minus this. Of course, you may get positive, negative values, no problem. So let's just find out what is the balance factor for each node. Then you will understand the dashes put inside the node. There are no values. This is a binary search tree. Now look at this node. What is the height of its left subtree? Is null or 0. This is also 0. So 0 minus 0, so it remains 0. So when the values are 0, so you get a straight line. So if there is one towards the right more, then you get a right line. If one towards the left, you get a left line. Or you can also get double lines to the right, double lines to the left. So that's how the lines are marked. So when you go through this, you will understand. So here 0 minus 0, so it is 0, so you have a straight line. Here this is 0 left minus this, so here there is one towards the right, so we have a straight line marked towards the right. Here again left is 0, but here there is 1 2, so there are 2 towards the right. So if you put value wise, if you are doing minus, it would be 0 here. Here it would be, if it is left minus right, it would be 0 minus or minus 1. Here would be minus 2. So 2 towards the right. Similarly here, this is 1 minus 1, 2, 3. So again 1 minus 3. So you have 2 towards the right. So we have 2 lines towards the right. And here it is 0 minus 0. So a balance factor. So AVL tree has got this property. Okay, so it should not be more than more than 1, maximum. Not the difference should not be more than 1. So here if you look, this node is AVL. Okay, this node is AVL, but here it is not AVL, not AVL. So this tree is not AVL because at every node it has to keep to this property. So some books you might find a definition or explanation saying that AVL tree is one that has a balance factor. No, that is not correct. Every tree, every node has a balance factor, but in binary AVL tree, what is the balance factor has to be within these limits. Okay, so what happens when a tree, a binary search tree or a non-AVL tree is given? Let's say a tree in which it is not AVL. So when you have a non-AVL tree, we need to convert it to make it into an AVL in nature. So we do 2 operations for that. They are called left rotation. The operations are called rotations. So we have a left rotation and right rotation, which are the main operations. So we will take an example and see how these operations are done in order to convert a non-AVL tree to an AVL tree. Now, so this is let us just go through this picture. You will understand left and right rotation. Simple. Let's consider this tree which is here. Okay. Now this is rooted at y, and here there is a node named x. Now the height towards the left is 1, so here there is a subtree t1. It could be a subtree or a single node. So this height is 1, and towards this there is a node, and there are 2 subtrees. So if you look at the balance factor for this, it will be 1 minus 1. So this is a 0 balance factor. Here it is 1 minus, so 1, 2, so 1 towards the right. So this is still AVL, no problem. All the nodes are AVL in nature. Now let us imagine we add a node at T3. Okay, so that means height increases by 1 at T3. So this is a picture. When height has increased, T3 increases, so the balance factor will change. That means x, now the balance factor here will be 1 minus, so this is 2, because there are 2, so there will be 1 towards this side But look here, here it will be 1 minus 1, 2, 3, which means you will get 2 towards the right. Now, so if you look at this picture, the tree rooted at y has changed, or it is not AVL, which means this tree is not AVL. So in order to do a conversion when the node has grown in its right side, what we do is we do what is called a left rotation. Okay, so we do a left rotation of this tree. So what does it do? What it does is actually you push y down and bring x up. That is what actually happens. So when you bring x up, y gets connected to x left side, and this will get connected to y. Okay. So if you look here, this is the rotated picture. So x goes up, x from here goes up, x goes up, and y gets pushed down. Okay, and y gets pushed down, so y's right side is free. So this node of x left gets connected to y's right, and y gets connected to x. So now this is a resultant rotated, left rotated tree, and if you look here, this value is 0, 1, minus 1, so this is 0. Here it is. Now at x it is, if you look, 1, 2, so 2 minus again 1, 2, so this also is 0. So this resultant tree is AVL in nature. So if you want a little definition, a little confusing, so this is a definition for a left rotation. So it pushes a node y down and to the left. So we are pushing node y down and to the left to balance the tree. That is, what happens is this, it's a little play of words. Y's right replaces y, and y's right child's left child becomes y's right child. I shall not explain. You look at the picture. I think it should explain to you, okay, how the replacing takes place. Nothing, pushing the y down, x up, and y gets connected to x, and y's right is free. So x left becomes y's right now. So if you look at an algorithm, here is given, suppose you pass the node y, x is a temporary node only, don't worry, and now y is given, we know x, but when we look at the algorithm, this x is a temporary node which is defined. So I'm passing y. So how the rotation takes place, the left rotation, x becomes y's right, and y's right becomes x left. So now x becomes y's right, and y's right becomes x left becomes y, and return x, that is a new road. So one way to understand is whatever comes on the right comes on the left next. So if you look against this rotation, I think this algorithm is clear. So this is a left rotation. Similarly, I think I need not explain, we have a right rotation. The right rotation is when the tree grows on the left side. Just the same, I think the picture is, this is only a mirror image of the same picture, but of course nodes are different. So here T3, it grows here. So we do what is called a right rotation. So here what happens is y is, so you can take the same words, replace all the right and left mutually. So y gets pushed to the right and x goes up. So that is the operation. So we have x now and T3 here. So x is pushed up and y goes to the right and down, and x right child becomes y's left child now. Okay, so we have, so if you look at the balance factor here, this of course is 0, and here it is 1, 2, so 2 minus 1, 2. Okay, so here all the nodes are AVL in nature, whereas here it was not AVL. So for example, here it would be 2 minus 1, so it would be 1 this way, but here 1, 2, 3, 3 minus 1, which means this side it was not AVL. So y we have rotated and made. So these are the two rotations sometimes asked as theory question. So what is an AVL? How do you convert the two operations? Mostly the left and right rotation. Thank you.